Let us look at two specific types of spread spectrum. One is direct sequence, the other one is frequency hopping. So what is direct sequence spread spectrum technique? DSSS is a transmission technology where the user data signal at the sending station is mixed with a high data rate bit spreading sequence or chipping code. This maps the user data in chunks of chips according to the spreading ratio. In the picture that is shown in the slide, the data rate is at 19.2 kilobits per second and the spreading happens at 1.2288 megachips per second. This picture shows the relationship between bit and chip. For a data of 1 bit, the output is 128 chips at 1.2288 megachips per second. The chipping code provides a redundant bit pattern for each info bit that is transmitted. This spreading effect increases the signal's resistance to interference. If, for example, one or more bits in the pattern are damaged during transmission, the original data can still be recovered due to the inherent redundancy of the transmission. Refer to the next figure on the slide. The time domain and the frequency domain representation of all three signals are shown in this figure. This is spread spectrum. Now what is chip? Chip in CDMA refers to binary digits transmitted over the RF link. Chip is a phenomena which is related to the RF transmission. It is distinct from bit. Bit is totally different and chip is totally different. The chip rate in IS-95 is 1.2288 megahertz or megachips per second. Each bit is represented by many chips, and if a majority of the chips get through, then the bit can be reconstructed properly at the receiver. When we use an 8K vocoder such as EVRC and a 1.2288 megabits per second spreading sequence, there are 128 chips for each bit. The multiplication will not be exact since additional control bits are also transmitted. Chips do not contain data. This is very important. Please note, data is separate and chips are separate. We have seen direct sequence spread spectrum. Now let us look at frequency hopping spread spectrum. What is this? Just look at the animation. Frequency hopping spread spectrum is a method in which the final RF carrier is rapidly switched or hopped around among many frequency channels, employing a pseudo-random sequence known to both transmitter and receiver. This is frequency hopping code division multiple access scheme. Please look at the animation. The signal of user 1 will follow a particular frequency hopping scheme based on a particular pseudo-random sequence. The carrier frequencies are rapidly switched to different values based on this pseudo-random sequence. For example, user 1 will have his carrier frequency sequence rapidly hopping around every 1 millisecond, such as maybe 800 MHz, 802 MHz, 824 MHz, 809 MHz, and 818 MHz, etc., etc. On the other hand, the signal of user 2 will follow a different frequency hopping scheme based on another pseudo-random sequence. For example, user 2's frequencies will be hopping around rapidly every 1 millisecond, such as 800 MHz, 822 MHz, 814 MHz, 802 MHz, 817 MHz, etc. Please note that at any given instant, for a short duration, two users may have the same carrier frequency. But over one complete cycle of a PRBS code, that is 64 bits, two users will never have the same sequence of frequencies. In this example, you can see user 1 and user 2 for a very short duration in the first hop share the same frequency 800 MHz. But if you look at the complete sequence spread over 64 bits, the carrier frequency hopping pattern will never be same between two users. At the receiver, the appropriate user will deploy the appropriate pseudo-random sequence and decode the signal. This is frequency hopping spread spectrum scheme. So let us look at this animation. This clearly brings out the role of codes in CDMA. As we know, users in CDMA within a cell are uniquely separated from each other through what is known as Walsh codes, and these Walsh codes are 64-bit length. Next one is the user's coded signals are further spread by high bitrate PN codes of the cell. These PN codes have two roles. One is they spread the user signals, and the other role is they differentiate one cell from the others. Cell separation is by PN codes and user separation is by Walsh codes. Please remember this. Okay, let's move on with this example. In this example, user 1's data is U1 and her Walsh code is C1. User 1, we presume, is a lady and she is the calling party. User 1's speech U1 is coded by Walsh code C1 and the combination is of course U1 C1. Similarly, there are obviously several other users in this cell whose combination codes are U2 C2, U3 C3, U4 C4 and so on. All these codes are sent over the air by the mobile simultaneously in the uplink and received by the base station. What happens in the downlink? In the downlink, the base station broadcasts several signals simultaneously for all these mobiles with combination codes we have seen earlier, such as U1 C1, U2 C2, U3 C3 and so on. User 1 receives U1 C1 and decodes with her Walsh code C1 and obviously gets back the speech U1. But we also said there are a number of combination codes over there such as U1 C1, U2 C2, U3 C3 and so on. What happens if user 1 tries to decode one such signal U2 C2 which is meant for some other user, let's say user 2. User 1 receives U2 C2 meant for user 2 and tries to decode with her Walsh code C1. The resultant U2 C2 multiplied with C1 will be equal to 0. That means user 1 cannot decode signal which is meant for user 2 and so on and on. A signal meant for any specific user cannot be decoded by any other user in the network. That is the principle of this. U2 C2 multiplied by C1 will be 0. U2 C2 multiplied by C2 itself will be U2. U3 C3 multiplied by C1 will be 0, whereas U3 C3 multiplied by C3 itself will be U3 and so on. Therefore, what is CDMA all about? Let us try and quickly recap what we have seen so far. Look at the figure. First property is same frequency for all. All users use the same frequency carrier and communicate at the same time. There is no frequency division multiplexing or no time division multiplexing. All CDMA users will use the same frequency unlike GSM. In CDMA, very often many cells will share the same frequency. There is no frequency reuse. The second property, fellow users interfere with you. In CDMA, the interference comes from the users around you, most probably belonging to the same cell or same network as yours. In other words, your friends or your enemies. The third property, codes for noise performance. The superior noise performance in CDMA mainly comes about due to spread spectrum technique employed in CDMA. CDMA uses Walsh codes and pseudorandom codes to spread the signal to get this noise interference advantage. The next property is codes for cell separation. CDMA uses pseudorandom shortcodes to separate one cell from another. Codes for user separation. CDMA deploys Walsh codes to separate one user from the other one. Walsh code for user separation, pseudorandom codes for cell separation. Each user is a small voice in a big shouting crowd but armed with a unique code. That is CDMA for you.